Hello, and welcome to today's demo from Introspect Technology. Today, we'll be demonstrating how to inject sinusoidal jitter onto an output waveform generated by the SV1C Personalized SerDes Tester. Jitter injection is a feature available in several of our Introspect products, and it's very easy to program this using the Introspect ESP software interface. To begin, here's a quick overview of the SV1C Personalized SerDes Tester product that we'll be looking at today. The SV1C is an 8-channel test system. It has 8 pattern generators and 8 BERT detectors, and it's capable of arbitrary pattern generation. It also has fully integrated jitter injection on all of its lanes. The setup for today's demo is shown here. The SV1C will be connected directly to a high bandwidth scope. We're going to program the SV1C pattern generators to add sinusoidal jitter injection, and we're going to look at the output waveforms on the scope. So let's take a look at the software now. On the left side of the screen, you'll see that I have the Introspect software open, and on the right side, I have 3 waveforms already set up on the scope. The first waveform is the differential output signal of the channel 1 of the SV1C. As you can see, the SV1C generator is already running. The second signal is an eye diagram showing the differential eye opening from the signal on channel 1. The signal here is 2.4 gigabits per second, and the pattern I'm running is PRBS7. And the default eye opening here is about 400 picoseconds. And finally, at the bottom, you can see there's a tie waveform. It's a flat trace as shown here. It's just a waveform that shows the long-term trend of the edge locations from channel 1. If we inject sinusoidal jitter on channel 1, we'll be able to track the amplitude and the frequency of the jitter by observing this trend. The eye diagram and the trend waveform are 2 very good ways of observing the jitter waveform on the scope. Now, there's currently no jitter injection on the signal, and so first I'll show how easy it is to create the component to perform jitter injection. If you're familiar with the Introspect software, you'll be familiar with this interface on the left side of the screen. There's a params tab where you can prepare and execute your Python scripts. There's a log tab which shows a running log of the SV1C operation during test execution. And there's a results tab which can be used to view analysis results. For today, I'm just going to focus on the params tab. On this params tab, there are 3 window panes. At the bottom, there's a test procedure window, which is where you would write your test script. And in this case, I'm simply setting the data rate with the global clock config component, and I'm starting the TX output by setting a TX channel list. On the top left, you'll see a components window. And there's a TX channel list component, which has a number of properties, as they're shown on the right. There's a jitter injection property, and right now it's not set. So right now there is no jitter injection on the signal. But if I click on this property, I can create a hierarchical component which controls the jitter injection. I'll do that now. Now, the component itself has 3 fields. There is a sinusoidal jitter frequency in megahertz, a sinusoidal jitter amplitude in picoseconds, and there's a random jitter amplitude, which we won't be looking at here, but this field allows us to set an RJ RMS amplitude. Now, the component above this, global clock config, is where we've set the data rate to 2.4 gigabits per second. Notice that the UI given here was 417 picoseconds. So let's set sinusoidal jitter amplitude to about half of that unit interval, say for 200 picoseconds, and let's set the sinusoidal jitter frequency to, say, 10 megahertz. The jitter injection component is called by the TX channel list component, and the TX channel list is called in the test procedure down at the bottom. So to start jitter injection, we'll just hit the run button, and then we can watch on the oscilloscope screen. what you see here immediately is that the eye has closed by about 50%, as expected, due to the jitter injection of half a UI. And if we look at the tie waveform, and I'll adjust the scale here, and I'll hit stop, you can see the sinusoidal jitter injection waveform. It has an amplitude of about 200 picoseconds, and it has a sinusoidal period of about 100 nanoseconds, which is exactly what we expect for a 10 megahertz sine wave. And for this plot, you can see the signal purity of the injected sinusoidal waveform. And the SV1C generator output will run continuously, and the jitter injection will continue to be applied until I issue other commands from the SV1C through software. Now, we can change the frequency of the injected jitter. For example, we can set the jitter frequency to be 25 megahertz and observe the tie waveform. I'll press run, and I will adjust the scale. And you can see that we now have an amplitude of 400 picoseconds and a period of 40 nanoseconds. So that's 25 megahertz as expected. And now we can slow things down. I'll reduce the frequency of the jitter injection to 1 megahertz and observe the tie waveform. So again, I'll have to adjust the scale, and you can see that we now have a period of 1000 nanoseconds. That's 1 megahertz of jitter injection, as expected. And finally, I'll create a quick loop which adjusts the amplitude of the jitter injection and observe the results on a scope. The loop could be written like this. We can start with a small amount of jitter. You can see it starts with 50 picoseconds, and that will result in significantly less horizontal eye closure on the eye diagram. And then we'll increase the jitter all the way up to 400 picoseconds. That will almost entirely close the eye. So I hit run, and I'm going to hit clear. And you can see that we're going to be adding progressively more jitter onto the signal. You can see the tie waveform below, and you can see exactly how that closes the eye in the eye diagram. Until finally, we get to 400 picoseconds of jitter, which almost closes the eye entirely. So this has been a very short demo showing how we can inject jitter onto the pattern generator of the SV1C. We've shown the signal integrity of the SV1C output eye diagram, before and after jitter injection, and you can see the signal integrity of the sinusoidal jitter waveforms, and you can see the eye closure that results. But most importantly, you can see how easy it is to use the Introspect ESP software tools to set up and test the signals that you require. Thanks for your attention.